Good afternoon, everyone. Welcome to today's Samvaad by Professor Das. It is an honor and privilege to introduce Professor Das, who has not only been a valued friend but also a mentor to pretty much everyone in the institute and definitely to people working in the area of networking. Professor Das has taught and continues to teach several courses for both MTech as well as IMTech students. His main areas of research interest are IoT and wireless access network, specifically the MAC, quality of service, and power savings. He has more than 110 peer-reviewed papers in different transactions, journals, as well as international conferences. There are several patents under review. He has contributed 3 ideas to IEEE 802.16m, which is WiMAX, broadband wireless standard. He is actively involved in several sponsored projects in the networking communication lab. Some of them are, I'll just list a few: smart semi-public buildings, IoT internetworking, green communication, TV white space, and so on. He has received Professor K. Srinivasan Memorial Award in 2017 for excellent teaching in the areas of telecommunications from IIT. He has also received Global IEEE MGA Achievement Award. He is a fellow IIT, fellow IE, and senior member of IEEE. He was the chairman of IIIT-Bangalore section, and he has been involved in many of the government organizations. I welcome Professor Das for his talk today on network slicing for 5G.
Thank you. Thank you, Professor Jyotsna, for the kind introduction, and thanks to Dean R&D, Dr. Srinath, for starting this series of wonderful talks by my esteemed colleagues previously, and so many to come in. And my talks has 2 parts. The first part is on the network slicing for the 5G, and please stop me if you have any questions in between. And in this talk, I'll be mainly talking about introduction, why the present access network and backbone architecture, how it is now, and from there overall you will get a picture worldwide how it is, and in India how it is, and US how it is, and overall. From there I will take you around that why 5G required, why present network cannot support 5G, and why we are thinking of a new architecture or new topology. That is very important to understand this transition, why we are moving towards that conceptual transition. Then I will take the 5G directions like evolutions view and service view. These are the 2 views where the people are talking about, and a couple of technologies and research challenges. So what are the directions the researchers are possible and going on. So now look at the present access network and backbone network. What is access network? When we were students, we used to call it as a local area network. There was only classical one local area network across the globe. That was classical Ethernet, and that was wired network. But when Wi-Fi came in, that was wireless. So in 2002 onwards, people said, hey, wireless is now in the local area network, wired is in local area network. Let us give a new name called access network. Access network means same as LAN, but your node called laptop, UEs, means mobile, or your any IoT sensor get access to the network. That is access network. And backbone means the behind your access point or base station till the final destination base station or access point is called backbone. Let us consider that as a backbone. And after reaching the base station, again the last mile is again access network. Okay, so between 2 access network, there is the backbone. So I will be talking about the backbone architecture and present access networks, and 5G will address changes in access and backbone both. So 5G is addressing both end-to-end communications architecture. Okay, so now if I look at these 2, backbone is 99.5%, 99.5% or more is optical network. So we don't see that, so we don't feel that. But if it is, but 0.5% is your satellite communications and all kind of things, wireless maybe, but 99.5 because it gives tremendous bandwidth and all kind of things. So no alternative. And access network is now 50-50. Still wireless is maturing, still maturing. So till it gives 1 gigabit per user, till that time we are using some places optical and copper. So 50-50 access networks. Okay. So let me go to the next step to show you that how the overall pictures looks like now. So this is your access part. 3G, GSM is 2G, GPRS is 2.5G. 3G, 4G, 4.5G means the LTE what you see now. Next will come LTE-Advanced, not yet deployed anywhere in the world. So after that will come is the 5G, and if these are your access networks, and this is your Wi-Fi, UMTS, and some part is satellite. Those who are in the sea, the ships and all in the sea and all connected by satellite. Even though in the deserts in Australia, some part which is not easy to pull the fiber there are connected by the satellite. And but those are so these are your access network. From here you get access, and this is your IP backbone, starting behind your access network to till the final destinations. And here you can see another set is called your servers, like Google server, Gmail servers, your ticket booking servers, your medical servers. Any servers are on this part of the world. So this IP backbone is your optical network. Okay, so this is your overall network architecture looks like. Now I'll bringing you to Indian example. You all of us in the campus use internet, and we get bandwidth from a network called NKN, National Knowledge Network. And this is your this is the India map, which is not come out clearly. And these lines, what you see, it is not the boundary of your country. It is all fiber laid down across the country. And BSNL is the maximum fiber across the countries from the BSNL. Next comes your Airtel and followed by Reliance and all. And if our knowledge network major bandwidth provider is BSNL, and how it is being connected, this is a practical picture at present what we are using. There are 7 core nodes we have in this country. Bangalore is one of them. Mumbai, Delhi, Guwahati, Hyderabad, Kolkata, Chennai. This core node is connected. These colors, so you see, these are the fibers connected with the different lambdas. And these core nodes are connected to this. You can see these are state capitals. All the 30 state capitals, all are not shown at here 30. So for the complexity of the picture, reduce the complexity of pictures. And below that you see these are the district headquarters. And below that block, then Taluk, then Gram Panchayat is connected now by the fiber, by these NOFN, National Optical Fiber Networks and all. So why I am showing this, if I am sitting at Bangalore, then how I am connected to the, say if I am sending an email to the Delhi, so by here in the campus from at IIIT here I am connected to the core networks, it goes to the Delhi, and now IIT Delhi, somebody, my friend, I am sending mail and connected like this. So this is one way I am connected. So similarly, if you look at the United States, you see these are from AT&T. There's around 10 people are there in US. They have laid down fiber across the US to reduce the complexity. I have taken the AT&Ts. This is the fiber connections, and these are the you can see here the international gateways in San Francisco. This is Los Angeles. This is from New York. These are the international gateway Florida, which goes out from the US to the other part of the world. In India, we have gateways are one in Mumbai, one in Chennai. If I go to the international outside of the India, okay. So now, why I am showing this, because I want to feel you that physically I have to traverse from, if I want to send from Bangalore to a mail to somewhere in the San Francisco or vice versa, somebody is talking over the phone or sending mails, videos, then how I traverse that, then how this architecture is complex, and what is the speed I need, delay I need, those for a feeling, these are the pictures. So I traverse so many kilometers to reach. So here, how I reach here, look at this. This is the submarine, under the water, the fiber has gone and it reaches here. So if you look at it from India, from India to San Francisco is by aerial distance is 13,990 kilometers. But it doesn't go like that. As a fiber, from here I start, from Chennai, I go to Singapore, so to Japan to this, which is going, it has come out here. Through Pacific, you see it is coming out and entering it to San Francisco at here. So it is around 15,000 kilometers or more than that in one way. So what is the delay now? So now I showed you India map, I showed you US map, now I show you submarine map. So I am on a 4G phone, I am talking to somebody on the US in San Francisco. What is the expected delay? 150 milliseconds. Yes, this is standard says 150 milliseconds. I say hello, 150 milliseconds is shown to the destination one way. So it is so many routers in between. I only showed you the fiber. There are some n number of routers, switches, and all kind of things. This is the voice. Voice is much higher delay. If you are playing games, video games, it is 50 milliseconds now, present standard. I am not talking about 5G. 5G is much less. And I will show you some example use cases that the present architecture, whether able to give or not, or shall we move to 5G, those are the questions I go for. So now you understood that how much I traverse to reach the destination and what is my requirement, 150 milliseconds for voice, which is higher delay with respect to games and other kind of things. So as usual, now I am back again. I bring you back to my first figures, which I showed you the different kind of pictures. The network is divided into 4 parts. Again, I am going on quickly to tell you what to. So I start from you. This is user equipment like your mobile, IoT devices. Here I have written your laptops and all. And your server is some part of the world. Your Gmail, you are going to Amazon, or you are going to anything, a data center. So there are how many networks I am crossing. Look at this. I am crossing an access network to reach this base station. Base station behind optical network, IP backbone. This is called core network. This is called access network. Then I enter into the data center. Data center has its own network, and it takes its own time to fetch and come back and tell you, hey, this is the information which you are searching for. So these are the so many networks I cross, but delays are in milliseconds. Okay, so now why 5G now? Then this is the overall picture I showed you with the fiber and or wireless and all, and wireless has an extra problem. If I transmit due to the channel problem, channel condition bad, my voice may not reach to the base station. Again, I have to retransmit. So I get delayed that 20 milliseconds by a couple of retransmissions. So now then why 5G? How the 5G is going to help me and all. So need of flexible 5G architecture to accommodate diverse use cases. So the use cases have diverse. Why? Previously there was only voice, then SMS, then video, then telnet came, then FTP came, this much. But now so much IoT devices, now you are talking about robotic operations. You are talking driverless cars. Have you thought of what is the delay now we are expecting from the network? Who will give us that delay? So those kind of things is called diverse use cases services to achieve all our requirements. It has changed a lot. To achieve to achieve this above diverse things, network slicing will play a crucial role. We'll discuss shortly. I written discuss shortly how this network slicing will help us the one possible solution to achieve these diverse use cases. Now coming to the key 5G use cases and requirements. Let us try to understand what are the requirements of the 5G. What 5G is expecting from us and what are the requirements. Look at this. International Telecom Union, that is ITU, which makes all the telecom standards, and 5G PPP. This is a new thing you must have heard. 3G PPP you have heard, third generation partner. This is the 5G, which is doing for the 5th generation. Public-private partnership have provided 3 broad use cases. Families. Family, what is used? Families means under this each family there are n number of use cases are there, not 1 or 2. One, the enhanced mobile broadband, which is the mobile broadband is there, as I said, voice call should reach in 150 milliseconds. Now 4G is saying 5G may say it will be 10 milliseconds or 15 milliseconds. Video should be so much less jitter and so less milliseconds. Massive machine type communications, IoT, cloud to cloud, cloud to fog, etc. These are machine to machine communication. It means there is no human interaction at all. Your driverless car doesn't have a human interaction at all, and delay will be 1 millisecond or less than that. Somebody comes in front of me, I have to push the brake. So network part is maybe 1 millisecond. Critical communications, some IoT based critical communications and all. So if under these 3 families, this is the picture the 5G researchers are now come out. If you go far away from the center, then you are more critical. Let us take this color: machine to machine communication, critical communication, mobile communication. So and critical communication, let me start from the critical. The yellow color is critical. This is yellow color, you see. So critical communication means latency has to be very less because it is farthest away from the center, means latency is less. Mobility is needed. If a critical ambulance is moving, mobility is needed. And reliability, there should not be any loss of the packets. The reliability also maximum. If I look at this blue color machine to machine communication, connection density. Those IoT devices will be sprinkled around so many devices, so densely they are being thrown across these IoT devices. So density of the number of nodes will be much higher than the user mobile phone. So how they will get connectivity? One of the research work was on that. I will show you 30,000 IoT devices, only IoT devices, only one kind of smart meters in a 1 square kilometer. And the power goes off in the smart meter. All 30,000 wants to talk to the base station. Hey, power is gone. 30,000 within that 300 milliseconds, how it will be successful? They will collide. All the messages, how to make them successful? So those kind of target given by the ANSI, American National Standard, has given that this is our target to meet. Okay, so this is the connection like that. So mobile has also the user data rate and latency, all kind of things. So to meet this kind of things, now these 3 broad families, can this existing network can give yes or no? If yes, how If no, why? So that I will discuss now. So new use cases and why flexible architecture. Now look at this. The use cases can range from general broadband access with global coverage, specialized sensors, extreme mobility. Use cases are these three. General broadband access with global coverage, or now we have a broadband and mobile networks with a global coverage, and specialized sensors and extreme mobilities. The utter differences between the use cases demand heterogeneous requirement for the networks. The utter heterogeneous means, as I showed you in the previous picture, this heterogeneous requirement of these three families, and one needs connection density, one is latency, one is mobility, one is user data rate. So three colors needs three different things. Can one kind of jacketed network, which is the same protocol, same set of modulation dimension techniques, same things, can give me all the three? Or I have to think about three different networks. If I have to think about three different networks, my cost will go up. So can I have the existing network infrastructure and slice that? Means this one kind of category will use this slice, second category, but infrastructure remains same. But then I have to do a paradigm shift in my architecture. So people are thinking in that direction now. So now coming to that point, the keeping above new requirements of use case in mind, alternative architecture are proposed and R&D to be done for the next few years. The dot is means 5 to 10 years. At least research and R&D has to be done to think, hey, already fiber have laid down, medium I cannot remove, laid down again 3 times for 3 different networks. Routers are there, switches are there, new requirements are coming. This existing router may not work, but I have to deploy some next generation router which I can change by software. Some new things comes, and then I have to make slices. Okay, this family have this slice, this family has this slice, this on the same infrastructure. This does not include any satellite communication. Satellite communication doesn't happen much, very less. In my starting of my talk, I said 99.5 is on the optical, 0.5% is on, less than that is on satellite, because satellite doesn't have so much bandwidth, which fiber can give us. For multimedia communications, fiber is the best solution. So the question is valid, but when we 20-30 years, a lot of satellite communication, but it came down because of the optical. Only in those seas, on the ships in the seas or the deserts where I cannot pull fiber and all, satellite is used. But the density is very low. So now coming to this one is the R&D to be done for the next. So one of the strong contender architecture is network slicing, which I am hinting you for last 1 minute, 2 minutes. Why network slicing? What does slice means? And with the advent of new major technologies like software-defined network, SDN, network function virtualization, operation management, orchestration, huge research is going on in all these new technologies. Ultimately, they will help us to go for the slicing. But before going to the slicing, let me make you understand why the present network cannot give this 3 broad families things. So what is one size fits all architecture? I mean, one size means all user can fit into one architecture, which is now we have. So practically at present, no use case oriented architecture. I have all the use cases in the same. That means if I want to do voice call over internet, I use the same internet of the same set of protocols. If I do a video conferencing, same set of protocol. If I send an email, same set of protocol, which I'll show you. And if I do something, same set of protocol used, not changed. Means according to the requirement, Internet Engineering Task Force is the boss, ultimate boss of making any protocol of the top 5 layers. And bottom 2 layers, which we always hear about, we always talk about, is called 3GPP or 5GPP and IEEE. IEEE means this Wi-Fi is done by IEEE, 802.11 is Wi-Fi, 802.3 is Ethernet by IEEE. 3GPP means all these 3G phone, 4G phone, 5G phones, all this comes under this. But they talk about this bottom 2 layers. Okay, so now the standard body done this top 5 and bottom 2. Okay, now look at this. Why layering structure? This every one of us knows that if you want to solve any complex problem from one part, then you have to make list of functions I need to solve that complex problem, and I layered it logically when I have to solve one set of problems. So that means in what are the complexity in the network? Every 2 mobile is different hardware. Every 2 mobiles software is different. Somebody has iPhone operating system, somebody has Android. Android has n number of versions. iPhone has n number of versions. Hardware are different, RAM different. Your application, you may have a Windows running, somebody have a Linux running applications, but both want to talk. Similarly, routers are different. Hosts are different, routers are different, mediums are different. Someone is wireless, someone is in the wired, and all the routers from source to destinations are different. So much difference as each element is concerned, but I want to talk to you in 100 milliseconds. So to achieve that, we have done this layered structures. That let us not talk about the hardware and all. Let us make the functions. The functions should be similar in each system. All the functions should be same, that they can communicate to each other. So now look at this. This TCP, UDP, congestion control, for any application you pick up on the top, they will be picking up out of these 3. I have no separate UDP for different applications. I have no separate TCP for different applications requirements. There are 2 major protocols on the network layer routing till today called OSPF, Open Shortest Path First, which is used in the metropolitan area networks, small networks. And the moment you go to gateway, international gateways and all, or from one domain to the other, you by default is Border Gateway Protocol BGP for any kind of communications. So this is jacketed, means so many hundreds of applications, but I am jacketing them to only 2-3 protocols, which is not efficient. Even the data link layer, physical layer doing new modulation, demoralization techniques and all, they are moving fast, rapidly moving, but top 2 layers is shrinking us to narrow but very slow speed. This top transport layer, network layer is reducing our speed a lot. So it is a very difficult time now how to break down these 2. It's not possible because it's like a foundation of a house. If I want to break down the foundation, the whole building will collapse, whole communication will collapse. So there we have to do it very carefully, this part. So that is the ultimate aim of the 5G. So this is the one classical picture which we all of us know, to feel that all the layers are in the only end systems, and in between routers, switches have bottom 3 layers, only bottom 3 layers. So now look at the examples. I will give you the examples, then I will enter into the 5G. Look at the India-centric Aadhaar. Now people are saying in the airport Aadhaar device will be there. So there will be a device like this, Aadhaar, and you go put your thumb. No need of carrying your identity. Your nice photograph come on the display and with your name, and he will see the ticket is there, and you will be allowed inside. What is the delay? Because behind me 100 people are standing. No one will give me more than 1 second. If I stand for 2 seconds, hey, just picture say on back side people will shout. So if it is 1 second, if it is 1 second of end-to-end delay, that 1 second carries what? That 1 second carries network delay. When from airport, it will go to the data center one way. After reaching data center, it will search second part. Search is the delay at the data center, searching part, that is from 1.5 billion search, that is an algorithm there. Plus, after return path of the network, then display. Display takes good amount of time because from memory you have CPUs are there, it will come bring it to your display. So if you look at, if I this 1000 millisecond I divide by 3, these 3 network delays has delay, the network delay will be less than 300 milliseconds, which is pretty high with respect to other example I gave. So network delay is equal to 2 into the user device first mile delay, how I reach the base station, n number of hops, last mile network, all those together multiplied by 2y because I go and come back. So this together it is 300 milliseconds. This is one example. So that means I have to activate my UDP protocol or TCP protocol according to these applications, and the routing algorithm according to that, so I can go fast and come back fast. So general requirements are like this: a driverless car is a 1 millisecond. In India, it has to be less. Any moment, anybody can jump in front of you. So it has to be much less, I feel. And the remote surgeries I was reading, so it is less than a millisecond. So hence, service-centric architecture is a new concept. Previously, jacketed network is there, one network, whatever service you give, network has same, no change. But now they are telling no. As you start the service, network will be ready to give you a service-centric architecture end-to-end to meet your delays or throughputs or your requirements. So these are the things now driving hence the service-centric architecture, application, transport, network layer, data link layer, physical will be defined and optimized. If you are developing an application, for that a applications layer protocol will be defined, a transport layer protocol will be defined, a network layer protocol will be defined, a data link layer, physical, all 5 top to bottom will be defined, optimized. This is the performance, 1 millisecond. But it will go through the same infrastructure. How? Okay, that is 5G same. So now again I am going back to school, showing you some of the pictures. If I am here, I want to go to here. So this is the router. So these routers have 2 intra-autonomous system. Intra-autonomous, A stands for autonomous system, is here. Routing happens from here to here. This is inter-autonomous system, going from here to here. Again intra-autonomous, there is so many things happens which makes us slow. So look at this. Host 1, it goes intra-autonomous system routing, make you feel that why you are slow. And you reach that. This is the only routing part. I am not talking about transport layer, congestion control and all. I reach the destination. So now these delays, how to get rid of direction for the 5G. So architecture is equal to topology plus protocol in communications. So architecture has 2 parts. One is topology, how you are connected physically. Second part is the protocols, means communications rules gives me the architecture. So direction of the 5G systems and architecture. Worldwide, various standard bodies working on 5G system requirements and exact performance goal. 120 millisecond is my goal, or 100 millisecond is my goal. So how to design a 5G architecture for that? However, industry and academia are agreeing 2 following complementary views. So industry and academia moving in a same direction but the 2 complementary views. One is saying evolution. What is evolution? I have already 4G, spent so much money. I have already spent billions and billions of dollars for 4.5G. If 5G comes, it should smoothly integrate. That is evolutionary view. Another one, no, what I said, slicing. Cut it, make it new inventions, new innovations and all. But both will merge sometime. So this is 2 views, evolutionary views and service-oriented views, which I told you service-oriented view few slides back, is that if I have a driverless car, I need 1 millisecond, design the network applications layer, transport layer, new TCP, TCP1 for this, TCP2 for this, TCP3 for this, TCP4 for this, and for if my application belongs to TCP1, TCP1 will be activated. Someone TCP2 like that, okay. So in the service oriented view, so 2 views. So let me tell you the evolutionary view. What is that? So natural transition from 4G when 4G advanced means 4.5G to the 5G. Natural evolutions, how it will happen. So people are talking about traffic volume will go by 1000x. 1000 times it will increase next 10 years, and 100x will be devices. Now how many devices is there? 4 billion mobile. There are laptops, PCs, small sensors, but that will increase to 400 billion. Like that. Throughput will increase by 100 times. Delay will reduce by 100 times. Spectrum efficiency 2G to 4G is 30 times already done. 5G how much I don't know. Spectrum efficiency has gone up. Professor Sridhar can say he's here, and Professor Josna works a lot on this. So these are the so 5G they're expecting another 50-60 times. Spectrum efficiencies may go up according to the literature. So these are my evolution, smooth evolution for people are thinking of. Now the next one is which is service-oriented view, that slicing leads to slicing. Envisioned to cater wide range of services from traditional human-centric, from voice call to machine-type communication, as discussed in the previous. Machine-type means driverless car. Camera will see somebody is in front of me, he will press the brake. You are on the sitting backside reading papers. So these are machine type communication, which is 1 millisecond. So these kind of things, so it requires same physical infrastructure of network to take different forms depending on the service requirement. Same physical network means same fiber, same wireless medium, but routers and switches has to change according to the protocols. It will give me this one, service oriented kind of slicing, naturally to the notion of network slicing. So network slicing means service-oriented view required for a radical rethinking of existing mobile and backbone network architecture with more flexible and programmable network systems. So this is a completely radical rethinking. The service-oriented is saying, hey, the moment I start an application called a robotic operations from the hospital, next building is hospital, this building is IIIT-B, both are connected to the same router on the internet, but that internet router will serve me differently, serve that person differently. There the delay will be 1 millisecond, here the delay will be 150 milliseconds. So the same router then complete the transport layer protocol, that for that person will be different, routing protocol will be different, data link will be different, physical layer will be different, till the end destination. How to do that? It's not only this router, all n number of routers. So that is the thing called, this is the radical thinking, that is called service oriented view. To ever possible leveraging the new technologies like software defined network, network function virtualization, orchestration, operations, lot of things are coming up. So to give quickly the understanding, look at this. These pictures, if you look at, these are the same set of routers, same fibers connected to each other, and this red color means these are support slicing. So if you see, so same set, you see same set of connectivity architecture for 5G slice 1 smartphones. This one gives the for the smartphone connection, RAT1, radio access technology 1, like means 5G, this is Wi-Fi, radio access technology 2, and give you smartphone connectivity. This is slice 2 for the automotive, for the cars, device to device communications. Then this is for massive IoT. I sprinkled 30,000 IoT on a kilometer only radius house, but same infrastructure giving different services, different quality of service. Okay. So this is called slicing, the use case for the network. So existing one will be like there are other slices are there for different applications.
Evolutionary approach. They are saying they increase the performance by a factor of 100. How is it possible to do it?
Yeah. It is possible. Same question I asked when I was a student doing my presentation in 2008, 1995, 96. Is it possible that wireless speed will go from, in the Wi-Fi, it was in 1 MB, less than 1 MB. Now it is 1 gigabit. 10 gigabits now. In Wi-Fi in the lab is now 10 gigabit. Possible. That is the research. Looking at that, 1 MB to 10 gigs, so how many times? 10 to the power 9 into 10 by the 1 MB to 6 means 1,000 times gone up within 10 years. 15 years, sorry. Power. Similarly, power. Go ahead, please.
But the fixed line networks are different, right, compared to wireless. I mean, your physical layer is fixed.
Yes.
So, how do we know the existing physical layer will scale up to this?
Actually, the medium, that's a very good question. That is you see, medium is constant, fixed. These routers, transmitter and receivers are changing. For an example, when I was working, I have worked on my hand 1 lambda, means 1 wavelength, 10 gig in optical. Okay, and there are 32 lambdas, we multiplexed into 1 fiber, and other side 320 gigabit is coming out. Now, that same lambda is sending 100 gig. Okay, so you improve the transmission technologies, and you improve the receiving technologies. So, medium remains the same. What happened? So, 320 becomes 100 into 40. So, 40 fibers now can be, 40 lambdas can be multiplexed. So, it becomes your 4,000 gigs, 4 terabytes on a single fiber thin hair kind of diameter, 5 micron. So, medium is not the problem. Problem is here, transmitter and receiver. Go ahead, please.
Since most of the cases the party on the backbone. Since we are deploying superior physical layer, and
access particularly the wireless part.
So both these projects would like to find solutions for exploiting the magical thing only at the access spectrums, right? So for example, the evolutionary approach will try to use different multiple access scheme or different physical and medium access control in order to improve the throughput. Whereas in the case of service-oriented architecture, I will deploy a service-oriented architecture on the access network, which will speed up.
No. Speed up is a research which is speeding up. Say physical layer, the transmitter receiver innovations is per hertz number of bits is increasing, and also that everything is increasing and as usual. But the service oriented is saying if I am using a driverless car on the wireless, then I should be using this particular set of modulation demonstration techniques, these particular medium access control protocol, which will be different for email.
Not different. But still we are looking at only bottom two layers for improvement. Are we looking at
exactly opals? That is the biggest challenge. I said in my starting. So I said in the in between also that will be TCP1, TCP2, TCP3, TCP4, UDP1, UDP2, UDP3, different name, SCTCP or something like that. But there are a lot of research going on to define end-to-end like that. On the top of that, orchestration. Orchestration means, say I am sitting at here and I am calling you. He calls me. He's a boss here. He wants to transfer his goods from here to Delhi. He calls, I am at transport agencies. So he voice call. Then he asked me, do you have a truck? Previously what happened? Sir, please keep it. After 5 minutes I call you back. Now it is not. Same live call, I will touch the map on the call. I will find out where he is sitting. Then I will tell trucks. I will find out who are the trucks close to him empty. Not full empty. Then I will tell the truck, I'll bring truck driver, myself and him on the call, not disconnecting it. So these are orchestration. One by one, I added voice call with the Google Map, with the truck Google Map, and the maps, voice, videos, triangular conference. Then I tell truck driver bye, both of us discuss money matters, how much it will cost and all. So orchestration of the calls without disconnecting. So those things all will come up. Doctor is talking to another doctor, both are talking on the voice, suddenly they start operation on the patients, moves to the complete robotic operations. So this kind of orchestration, management, all will come in, and how to do that on the fly, that 5G will address, along with the slice. Got it? I'm not making little complex, that is the truth actually. Go ahead, Professor. Exactly, I'm coming to that. Hardware slicing will happen through the virtualization. I'm just another 2 slides away.
So different kinds of applications will have different network speeds. So I was just wondering what implication does for net neutrality?
Sorry?
For net neutrality, what implication?
That is a political issue. So that I'm not talking today, I'll talk another day. That is a political issue, means not political, it's a business issue actually. Policy issues, business issues. So I'm not talking about that. This talk is pure technology. So these are all leading towards all those things. Okay. Yeah, at present policy allows all these things. Till today, internet doesn't belong to anyone, but people are trying to hijack because $1 trillion business there. So that is the other way of Facebook, Google trying to hijack it. Now it will be little tight for them. So okay, so now coming to this point, those I am showing you the slices going through the same internet. So now coming to how this are, now I am giving the solutions to you. This is a very classical picture which we all know, the telecom network. How is telecom landline is the one of the best voice call till today, end to end, how it is achieved. So this is a voice telephone of yours, it is a telephone of your parents, you pick it up, talk to them, so clear voice. So this part is your data part. Now look at this. This is the control part on the top, and now this is a this dotted line you see, thick dotted line above is control layer. So your voice call goes straight first to the dialing to the control plane. He gives command exactly connected. This is the path, and it is a circuit switched one. So dedicated path, circuit switch knows how much bandwidth is needed, never changes. Done, voice call. But it is a huge invention, but it has lot of easy things. Means voice bandwidth is known, end to end, how much it is not doesn't fluctuates and all. So it becomes very easy. So now, but in present data network, which is internet, it is a completely different. Voice has a different packet size and different frequency I generate voice packets. Video, different packet size, different frequency I generate that. If I am sending some Google Maps and all, different frequency, different size. So there is a 3 statistics are there. Voice 1 statistics, video 1 statistics, map 1 statistics. So this is called statistical multiplexing. So I cannot predict how much traffic will come so easily according to orchestration example I gave. So lot of things, what happens if look at on the left side, it is your voice, you are here on the mobile, you come to the base station, here the control plane, here is the SDN controller, software defined network controllers, which will give command. These are futuristic internet, which is going to be that 5G is talking about. Then these are the switches will get connected till the destination is here. And he will only tell the path. This is the path you should follow. This is called SDN, software defined network architecture, for giving you the path, control signaling, that telling this one that this device is, hey, give this much of bandwidth. If you need more, again control signal will give. Now he was talking voice, suddenly I want to see Professor Parikh, Chetan Parikh nice face. So he will give the video through that. So control signal will come, video will be connected. So these are the things will be happening at here end to end. But now this is the thing you can see, challenges now coming. This is the wireless part, and I am in the 4G. This is the optical part which you are talking about. High bandwidth, high traffic, but there is not proper QoS is there like our 4G or 5G. So how to SDN controller, look at this, 2 SDN controller. SDN controller in the wireless part has to talk to SDN controller on the wired part. How to do that? So this is one of our work from the lab recently in December 27 got accepted, a dynamic QoS negotiation mechanism between wired and wireless SDN domains, 2 different domains end to end in this IEEE transition network and service management. So this is the work which talks about how to do that, what Professor Siddhar was asking.
What do you define QoS?
Huh?
How do you define QoS?
This quality of service means say end to end delay. End to end delay, throughput, these 2. Because a delay, if you are a real-time communication kind of example, delay is more sensitive than the throughput. Okay. So now we work on that. So now advantage of SDN as a routing decision made with a big picture in consideration, it become more and effective and optimum. And now this is, if any nodes fails, what is the pain? If you are working on a system like what, if we are asked to talk, Professor Tangaraju, if you are if you end to end, if one protocol in this router changed, next one manually changed, not automated. So any service provider, any new patches come, you have to give command manually. So what happens? It is very difficult. You have to shut down, make manually and all. So now those days are gone. SDN central controller will give command. All the nodes below him software will change automatically on the fly. Okay, so these kind of easy things, if new algorithms comes up, it is easy to change network application then and the reprogramming boxes. So now I am coming to the what Professor was asking. Now this SDN gives me the path, source to destination. It gives the commands to the switches, hey, I need this much of bandwidth, this much of your processing time. If you are using driverless car, your processing has to be much faster. You are given more cores, more dedicated operating systems to do much faster than your email going. But at present it is not possible. Futuristic, this is called the concept of called NFV, Network Function Virtualization. So Professor Sen asked me how the hardware will work. So I am done this picture capture for understanding from view from cloud computing. Previously, if you look at this hardware was there, the black one is hardware, operating system, one operating system and one application. So this was completely binded. Now what happened? Hardware is same, virtualization layer is there, the hypervisor and all kind of things. On the top of that, multiple application ways they have through virtualization connect to hardware. So as the applications demands more and more, this hardware provides them according to that memory and the computational time and all those things changes. So for that we go into those cloud computing and all concepts. Same concept networking is going to borrow for their hardware. So how it will happen? It will happen, network virtualization is the process of combining hardware and software network resources and network functionality like routers, switches, firewall, etc. into a single software based administrative entity. Single entity, and it will be sitting on the top. It will give a command, that control plane which I said, giving command to the hardware, hey, this new application is starting, you give this much of process time, this much of memory, this much of bandwidth at the switches or the routers, then he can cross through within a 1 millisecond through 10. And accordingly, it will give.
But the network elements will slow down, right, because of virtualization, because virtual machines are always slow in this.
That's true. That's true. But what will happen? But now in future, these are most likely, professors can say better, because if you're more software dependent, it will be slow. But FPGA and other kind of things may come, so that may give much faster command. Okay, much faster than that. So look at this. What will be there in NFV? All the, sir, please go ahead.
This includes RAN virtualization.
No, sir. So virtualization means RAN is one part of it. End-to-end, RAN has one virtualization part, which I'll show you. Those are radio access technologies and how we'll give. Always we all belong to that last mile, what you are asking, but backbone also. Virtualization will happen. Major is on the backbone. It is moving like this very nicely, like the tsunami comes from place of earthquake to the shore. It is moving like that. Already done in the data centers. These NFVs and SDN. Now it is coming to the backbone network. Then it will come to the last mile. It is moving towards us. Not reached yet. So research is now on the last mile and some extent in the backbone. So if you look at the switches, this is a sign of the switches, routers, this is a sign, load balancers, firewalls, all these activities of network by software can be done, by NFV can be done on the same box. Same box can do all activities by this. So this is the comparison which is shown from your classical server virtualization picture and the mapping it to the network virtualization. This is in 2001, this is 2012, it is on the other side of the board, so not showing. So it is going like load balancers, this is firewall, VLANs, all those things. So APIs, automated, like logical load balancer, logical firewall, logical routers, logical switches, virtual network. So command will come, hardware will provide them, all those things. So now leading how it looks like. So SDN and virtualization, NFV, SDN and NFV complements each other. They are very, software defined network is a controller. It will give command, hey, hardware and software, please give particular service from end to end. Please give me this much of processor, this much of bandwidth, this much of memory, and this much of all these things from here to here. I need this delay, 10 millisecond delay. And this command will go from here. Automatically these boxes will configure if it is available and give you the end-to-end connections. So this is the slicing is going to happen. So now coming close, that SDN is a typically thought of managing, automating tasks, and NFV is all about the provisioning of new network devices. And SDN may then be used to manage the virtual as well as existing physical devices. So now this SDN and NFV is these two. This is SDN gives managing and automating tasks. NFV is all about provisioning of new networking devices. So this one, when it gives the command to SDN, it will provide you those firewalls, routers, switches according to your requirement from the same box, same hardware. Technologies are management and observation, triced 5G state of architecture. These two combined will, along with the management and orchestration, will tries to give 5G state of architecture. These four means SDN, NFV, along with the operations. There's a huge operation issues, management issues are there, and orchestration. Like example I gave, the driver and a client talking, how they add, remove, all kind of things. So now I will quickly show you one slide, then I'll switch over to my other talk, state of the art in 5G network slicing.
SDN will affect which layer?
SDN is the control layer in the top. I'll show you next picture. Give me 1 minute, I'll show you. So the state of art for the 5G network slicing, this is the picture which I want to show you before I switch it over. So this is the generic framework for 5G accumulated from various possible architectures. So this people did all research for the 5G, gave final one that there are 3 layers. This is called infrastructure layer, where those hardwares will be there like your existing boxes, and this is called network functional layers, where you have a control plane, that SDN controllers and all will be there, user plane functions, configurations, life cycle. If I make a slice, how many years or months or seconds, milliseconds it will should exist. top of that is service layer. So service layer will tell the moment on your mobile you touch a video call or a voice call or a medical kind of emergency, the applications is generated. That is called service, called use case. That will go to the control plane, which is in the second layer. This configuration lifecycle control plane, that will give command to your physical infrastructure. Please make a slice from end to end to give this QoS, period. So this is the major, and to control this thing, this is the management and orchestration layer. It is connected to all three, life cycle and all. Okay, so this one I will stop at here, and now any question on 5G slicing, then I can give the answers, and the slides are also here. I am also here, and so anytime. It is actually logic of routing control plane. Like in the telecom, they used to find out the shortest path, but the internet it is different. It is a little different because it's a packet switching, and your voice may go in one direction, video may go other direction. They will mix up in according to the availability of the paths and all. And these are mostly on the routing and the availability of the resources in the below data plane, which is forwarding, hardcore forwarding the packets to the destination. So this will be the control plane work. Yeah, absolutely. So this is a talk about which I have mentioned on my mail. There will be part 1 and part 2. And part 1 is on the 5G slicing, where the research is going on for 4 or 5 years now, at least 5 years or 10 years. We don't know where it is moving on. And also we are also evolutionary process, 4G advanced. Now we have done some work on the 5G also, which I showed you one of the slides, that SDN Wi-Fi, SDN in the wireless, SDN in the controller in the WAD, how they talk to each other. I can forward those papers to see those in IEEE TNSM, transaction in TNSM. So now I am going to talk about power saving, another critical issue in the whole world, particularly India, where we do not have a power now and then. Okay, so power saving protocol base station and the dense IoT access, LTE-Advanced and beyond means 5G, how to do that. So I was thinking where to give talk, so I picked up last 2 years journal publications from the labs with the students, and this is the recent one which published in this last month, February 2018, in IEEE Transaction in Communication and Networking, in the optimization of bearing factor enabled extended access for energy saving in LTE-Advanced. Then Saptarshi and we all worked on a novel QoS, our medium access control for different scheduling algorithm with a self-organized network. How if the network is changing according to the channel conditions, then how the network have a scheduler changing. And Pradnya and Professor Bapat and myself working on smart home. This is a one work. Divakar, this work I showed you, and I made it green color this one because I'm going to talk about this one. The Prashant and Amudishan is here. Myself worked on optimal time spatial randomization on energy efficient IoT access. How 30,000 devices can access the base station within 300 milliseconds or a few seconds. So this was accepted in August 2017 IEEE transaction on TVT vehicular technology. So and then I'll be talking all these papers, different journals. Then I'll be talking about this one. This is a very Prashant on our works, the enhanced power saving semi-persistent scheduler for the voice. This is in IEEE transaction wireless communication. So these two green I will be presenting. In future, if time permits, others I can present. So let me start from this one. What motivated us? These are all 10 years of motivations, and motivation 10 years, but the work of one and a half years of solid work in the lab. So now motivations I'll tell, then existing link level challenges in 4G advanced base stations, proposed link level MAC to save power, and proposed MAC for high density IoT. Motivation is very much, you know, that how many base stations in this country has? It was 6 lakhs only 2 years back, 6 lakhs, 6 after that 5 zeros, okay. Now it is 8 lakhs, 2 lakhs increased within 1-2 years because thanks to Jio, okay. That will be 12 lakhs next 2.5 years, okay. So just doubling, we are 10, 15 years around 6 lakhs, now going to 12. I think Professor Sridhar may be knowing better than me on these issues, but this is the truth. Why I came to know? Because I go to, in sabbatical last summer, I was in Samsung. Samsung provides them the base station. So from there, I just over here, when they're eating over here these numbers, so this is the number now. Acute need for power saving. Why? This is the cause. Any base station, if you look at it, around 65% is base station. This is 65% is base station, and out of that, and base station emits 30 million tons of carbon dioxide, which is higher than anything your users and your other kind of. So this is the maximum power consumption, maximum carbon dioxide. Not only it drinks power, but it emits carbon dioxide so much, and not then this one. If you look at this, is very interesting. 60 watt is output because there are 3 antennas, 20 watt, 120 degree antennas angle. So 120, 120, 120. So three antennas output is 20 watts. So output is total 60 watt. Input is 1500 watts. So 60 watt by 1500 watt is efficiency. It is 3-4% only. Of course, because power amplifier is there, these ACs and all kind of things bring so much power. This is most painful from India point of view, this slide. Very painful from India point of view. This is not my slide, this is TRI's slides, TRI's numbers. If you look at 10% of the sites, cell sites have a 20 hours, more than 20 hours power. Only 10% in India. 20% is 16 to 20 hours of power. And 30% is 12 to 16 hours of power, conventional power. 25% 8 to 12, 15% less than 8 hours. Means if you go away from Bangalore 20 kilometers, only power comes for 4 to 5 hours. Okay. So if you look at bottom 3, if you add up 70% of them in an average has only 12% of power. Means rest of the 12 hours or more than 12 hours I am running the base station, 70% of the base station of this country by diesel generator. And it drinks close to 3 billion liters of diesel per year. And that emits what carbon dioxide? I don't know. That number we don't have. But the thing is, this is not true only for India. If I go to the many developing countries, underdeveloped, this is much worse. Means out of the 8 lakh base station, 6 lakh base station doesn't have power more than 12 hours. So how to save power? So saving the power, we went on working, thinking that which problem we will address. So everybody is addressing this. Hardware people are addressing, software people are addressing. We address from the network point of view. So from that we came out that there are component, link and networks. There are three ways we can save power in the network. Component means those hardwares. If I can save power on saving those hardwares. Link means this medium access control protocol. I am transmitting. If I efficiently transmit and consume less power, every bit I save power. So that is a huge, may come to huge numbers. And network means routing and all. So we are addressing link level 1. So by intelligent traffic scheduling by smartphones, how to intelligently traffic schedule that. So now look at this. We were talking on a phone, and if you are, this is the UE and this is the base station, and there are every frames are there. If there's a by frames, your voice goes from, or your data goes from you to base stations. Okay, and if there are 10 frames, and this is 10 millisecond. From here to here 10 millisecond. There are 10 frames. So that means one frame is 1 millisecond. And 1 millisecond is divided into 2 slots, slot 0 and slot 1. That means one slot is 0.5 millisecond. It's a very interesting problem. It is hardware and software mixed. How much time I have? 3:15 or 3:20, something like that? 15 minutes? Good. So now, so coming to the point is that if these are the frames, look at this. These are the 1 frame is your, 1 subframe is your 1 millisecond, 1 millisecond. Okay, how it transmitted, look at this. So now, if this is x-axis is your time, look at this picture very carefully. X-axis is your time, y-axis is your frequencies. The frequencies kilohertz. We have basebands where we modulate and transmit our voice or videos, data and all. So this is 1 millisecond. This is 1 millisecond according to the subframe, and this is your 180 kilohertz of frequency. 1 box. So to transmit a voice hello of a say 20 milliseconds comes 160 bytes, I need 3 kind of boxes to send that voice to from my UV to base station. Okay, and what is this black spots looks like? These black spots under these color lines are nothing but those are control channels. Wireless has n number of control channels which is written at here. All this here written at here. So if I want to transmit a voice in the next slots, here the control channel will be coming from base station asking you, hey, do you have a voice? You say yes by the control channel. Then your base station will allocate this PRBs. This is called physical resource blocks. That these 3 PRBs are for you, you transmit. If it doesn't say that another user will transmit, they will collide. So every PRB is well defined by the base station which you will transmit. Uplink, that there will be collision. So those black spots what you see are control channels. Okay. So now coming to the point. Coming to the point means when this picture is very look at this. If the base station is on, not transmitting anything, nothing, then it consumes power called P0. That is here. Look at this power is P0. This power is P0. That means I am not transmitting anything, P0. When I start transmitting, the more and more I transmit, this is excess, this is more and more, my power consumption goes up more and more. Very simple. So now what is our aim? Now our aim is, I'll give you the example first. When your laptop is, you are not doing anything, or your mobile, you are not talking anything, what happens? My mobile goes to sleep mode, the screen goes off, but that only you see. But inside hardware, what happened? If you took the heat picture image of that hardware, you will find only the clock side is on, a rest is completely dark. That means completely sleeping. That was not there in previously. Slowly people do a lot of how quickly they go to sleep. When you touch to on, quickly everything is on. Okay. So this is our aim. So we thought that if the base station is not talking, anything it is not sending, can I bring it to sleep? Then instead of P0, I will consume PS. So I will save this much of energy. But if somebody's voice comes to the base station and he has to transmit to me, and vice versa is true. If I am transmitting to the base station, he has to transmit to this side, base station has to wake up. So how fast he can wake up? So we have to take the help of the hardware people that, hey, tell us that how much it is working. So luckily we got some very positive answer from the hardware people. They told us that, hey, in 17 microsecond base station can go to sleep and it can wake up 17 microsecond. So I have a 1 millisecond, 17 microsecond if it is there, then in between the rest of the microsecond I can go to sleep and wake up. I save energy. These are because we are interacting with the hardware people in the different companies, they gave us a number. They don't know what is running in our brain. We took that number and we make this full research paper on that. So the dynamic scheduling and small packets going, limited PDCS resources. So let me tell you, small packet size. So every voice packet is generated from your UV. If this is your UV, means your mobile handset. You said hello. Every 20 hello, I said hello. 1 second I took. So every 20 millisecond, one voice packet goes. So hello packet will go as a 50 packet. Why? 1 second by 20 millisecond is your 50 packets. So 50 packets will be transmitted from here to base station to only transmit your hello. Okay. So with the practical example, I am telling you that. So if 20 millisecond one packet is going. So this is called semi-persistent scheduling. Why semi-persistent? Why? Because every 20 millisecond persistently I am transmitting, but while starting, when it will start, if some changes happen, so it is semi. Okay, control channel takes care of that. Now look at this picture. There are 3 users. This was the first concept. There were 3 users. The cycle is of 20 milliseconds. Look at this. 20 subframe is 20 milliseconds. 1 subframe 1 millisecond. So 1, 2, 3, 4, 5, 6, 7, 8, 9, up to 20. This is 20. In between that is not shown, all the 20 is 20. So this first user came here. He got these 3 blocks. He is transmitting at here. After a certain time, second user came, this green color, he is transmitting at here. Third color, it is here. Okay. The interesting part is, if you are on, you are consuming the full power of this 1 millisecond subframe completely. Even though you are not transmitting here, this is the white part, but you consume the full power. And you go to sleep in 17 microsecond at here and wake up at here before the 17 microsecond. Again, you receive this one. Base station is doing. So people thought how to optimize this. That means, one smart guy came out, hey, can I make the green at here? Then what will happen? Anyhow, I am consuming full power, then this one will be full white, I can save some energy. So let us wait the green to some amount of time, out of the 10 millisecond of waiting or 15 millisecond of waiting, after that push the green at here. Don't allow the green to go at here. So a smart person gave an idea. Very good paper, very nice idea. So now they came out with this idea. Look at this. This same picture I have here, drawn at here. Again, telling that there are 5 users, red, blue, green, light blue, yellow, 5 users, and they are repeating here every 20 milliseconds. That smart fellow did this. They said, hey, don't allow them to go whenever they are coming, club them. 1, 2, 3, 4, 1, 2, 3, 4, 5 users. Then how many slots are empty here now? Look at this. Here I used to consume 1 slot, 2 slot, 3 slot, 4 slots. Here how many slots I am consuming? 1, 2, 3. So 4th slot is empty. So I saved power here by this process. Very good idea. On this process, they saved 20% of energy in the base station, 20%. But they missed one thing, which we caught. What we caught, that I will explain you. What made our paper, IEEE wireless communication is a tough journal, very tough. What they missed is, look at this picture, then you will understand. Same picture I have expanded at here, continuously transmitting, expanded at here, okay. So now, 2 things they missed. Number one, if I have 20 users, how many columns I will fill up? 20, each column is 2 users, 20 users means 10 subframes will be filled. Very nice. But there was a problem. In the wireless, there is no guarantee that your packet will reach the destination. So if the negative act come or timeout, you have to retransmit. So in the LTE, it is 7 milliseconds. In the LTE, the retransmission happens within the 7 milliseconds. So in this case, what happens? If my 10 columns are full, 1, 2, 3, 4, like this n is set 10, n is set 10 full. So this first rows, the 1 packet is missed. I will try in the 8th sub column. 8 after the 7 millisecond means 8, but 8th one is full. So I am not able to retransmit. So retransmission became a problem. Point number 1. Point number 2. People say, hey, you retransmit where is empty, but where is empty, there was another problem. What is the problem? I need a control channel to inform the UE that this slot is empty for your retransmission. The control channel may be busy for something else, control channel may not be available. So there was a scarce, 2 problems happened. One, if I continuously fill up all the completely the subframe, my retransmission is a problem. When I get empty subframes, there my control channel is not available because it is busy for something else. So these 2 combinations we solved by our idea. What we did, this is the idea, very simple idea, but it is a good one in the sense that we said do not fill up completely, give some empty. How much empty? That was a question asked. How much? So find out the channel condition between the UE and the base station and find out the probability of error from your transmission and find out what is the probability of retransmission. Accordingly, you give the emptiness on the top. Then you can retransmit. That is one thing. Second thing is very interesting. Previous example, what you saw, they are filling up continuously. We said no, don't fill up the subframes continuously. How you fill it up? First you fill up the first one, then you fill up the second call, if comes 8th one, 8th subframe. Then because if any loss happens here, I will retransmit in the 8th, and if the 3rd packet comes, then 8 plus 7 is 15. So below you can see we completely restructured LTE advanced transmission slot filling. 1, 8, 15, 7 millisecond of gap. And then go to, if these are completely full, go to the 2, 9, 16, 7, then 3, 10, 17, then 4, 11. So like this 20 milliseconds is structuring changed. And that improved your efficiency 50% straight away. Previously only 95 calls for base station was going through. It was 95. Look at this here. Sorry, it was 95 here. And according to our idea, it went to 145 here. And power consumption also was the minimum. So these 2 things happen. Sorry. Please go ahead.
So the transmission probability is high.
No, this is actually taken according to available all accepted models of the channel and all. These are the things. Our aim was on the MAC protocol, medium access control protocol. So physical layer things, we took it from the other references and journals, hardware from another references, that 17 microns. Our is this one, contribution is this. How you will insert the voice into the subframes. That is our contributions. And
ultimately an NPR form, right? So you don't have it's not possible to get a straightforward optimal solution. So probably it falls in approximately angle.
yeah,
My guess is probably like 2 over 3.
yeah, you're right. You're right. It's not easy. So, so this is the way we solved it.
You are solving it for a specific set of data, right? You are given the for a specific base station, you know the
But yeah, you're right. But
optimizing the optimization is determined by the data.
that's true. But what Dr. Shisha is asking that because for what kind of modeling you use, how you did it, how you reached to this by theory and simulations and all. That's true. Yeah. Good one. So now I have only 2 minutes left according to yes. So I will just quickly go through the other problem. Very interesting one. This one. So this one I showed you. This is the other one, which is very much close to our present works of IoT. So many, as I said, 30,000 IoTs in a 1 square kilometer, and that very live example is smart meters. Every smart meter has now a SIM. Power goes immediately. They informs the and all, if it is connected by the 4G base stations, what will be your situations? So optimal time spatial randomization techniques for energy efficient IoT access LTE-Advanced. So Prashant, Amu, Adishan. So this was in August 2017 in TVT. So now quickly here is a need for address these issues that I have, and let me tell you a very another interesting practical problem. All of you have a mobile handsets. If you are a 4G phone, if you are not talking for a 10 seconds with the base station, either not talking or you are not downloading, not doing anything, your base station forgets you. Period. Okay. So now if the base station forgets you, if you want to start a communication, that first goes through something called a RACH process, random access channel process, that to authenticate you that I want to communicate. That RACH process is a 4-way handshaking. That means one, I'll send a RACH to the base station will, let me straightway take you there. Sorry. This one. This is the RACH, random access request RACH. Then the base station, this is base station, right side, left side is your UV, random access response, then terminal identification, message 3, then message for your connection resolution. After that, your dialing, everything starts, call goes through. So if your meter is not communicating always with the base station, 10 seconds, 20 seconds is nothing. You are only, so if you are synchronizedly, forget about the power goes. If I say all these areas meters should give me reading every half an hour, after exactly half an hour, all the meters will say, hey, I have consumed 2 kilowatts power. Power is only few bytes, this 2 kilowatts. But for doing that, I have to go through this 4 steps first, and 30,000 wants to communicate to the base station at the same time. Then what the problem is, there are only 54 preambles in 4G Advanced. 54 preambles and 3,000, 5,000, 10,000 meters on the smart IoT devices, and they may select same preamble and they transmit and they collide. How to solve that? So there was one very famous paper which was by Chang, which is accepted in a 3G 4 LTE Advanced standard called bitmap bearing and enabled EAB by Chang. And so we have done the other one, which is EAB BF, which is called bearing factor enabled EAB. This one is EAB BF performance is much better than BB, analyzed by us and just published in last month, February. It is a 2.5 years of work. So, so this is the algorithms, which is says that device activated, then bearing employed, means what is this bearing stands for? This is called PEAB, means probability. I run a probability in the node. If the probability is above that number, say 0.5, then it will not access the network. If it is below 0.5, it will access the network. And once you are said above the 0.5 means not accessing, after 16 seconds you will try, not in between. So like that. So like this is the algorithm written, and what the result found out? The result found out that this, you see there are three curves here. This is the collision part, this is the success part, and this is the total. Means collision plus success, this is the total how many nodes have tried. So it found that there is a collision, the expected collision number of devices pretty high. So to overcome that, we gave an idea. This is the idea. The idea is, sorry for the lack of time, I am not elaborating so much, but I'll elaborate the idea very vividly. So once we said the same macro base station was connected to all the UEs and the IoT devices. So as a result of which, when the 30,000 people are trying and 100 mobile handsets are there, 30,000, 100. 30,000 is the IoT devices, 100 is your UEs, phones trying, but my all get collided, phone also doesn't get through. So we said, okay, if you have a 20 megahertz frequency, for an example, 15 megahertz you give it to the macro base station, and 5 megahertz you give geographically divided by picocells, not overlapping. And these picocells or the femtocells are connected to IoT devices, and UE is not connected to the femtocells and picocells, and they are directly connected to the macro cells. So the frequency wise, space wise we differentiated them, and time wise we also differentiated them, and we found out that by doing this, these are the points I have written, whatever I explained to you. You can see here, if I increase the number of picocells, my collision is close to zero. There is almost no collision, and all are success. For the RATch, only for the RATch part. So this is the way we solved one of the long time problem. It was there from when I was working on the WiMAX in 2007, 8, 10 years back problem. This is solved by this time and frequency. If we do, then you can have these results. So this concludes my presentations and some of the futuristic works we are looking at, that in 5G, small base stations like picos and femtos for handling smartphones traffic. An interesting problem is to investigate if using those picos and femtos to manage IoT devices RATch request, how to do that, as well as their traffic along with the smartphones. So we are working on multiple things. We are working on LA, LTE assisted access. That means if I have a Wi-Fi access point, we have a LTE base station. If the LTE base station is very busy, how LTE base station can hand over some of my downloading to my Wi-Fi in the lab? So lot of things. This is a revolutionary process going on. Work is going on. Thank you.
So first of all, when you have a combinatorial number of different options and all the network elements are true.
Yeah.
Because each one, if you have only 5 and there are 50,000 elements all over the network, then the number will increase combinatorially.
Yeah.
How is that going to be handled?
You see, every devices will be registered with the access point or base stations. Okay, that is point number 1. Point number 2, the network will be divided into 2 parts, the services. One is called real time, one will be non-real time. In the real time, there will be different subsections. So when any device wants to communicate, number is high, so 30,000, 40,000, 10,000, whatever it may be. So that will go to the access point by this control signaling, what I showed to you in case of my slicing slides. Okay, so when you go there, let me go back to that. In this one, there are a couple of things will be added to these nodes. Those are called, one is called call acceptance. Call acceptance, not only voice call. If I want to send a data, this network is ready to take my data or not. Network has extra bandwidth. So whenever you initiate anything, this is your mobile handset, this small line mobile handset, or this is a mobile handset. You want to send a data, something, your temperature of the body or a voice call. The first it will come here and it will go to the control, this one, and he find out which destination you are going. He will find out from this control plane if this path is empty or not till the destination. Call admission, call classifications and all will come. Go ahead.
So do you consider IoT network using more of femtocells being deployed or CSS has?
Femtocells is coming in. And LTA, this LA is a stopgap kind of things. I have a huge argument when going on inside my brain. Also, 2-3 times I told in the lab also. Wi-Fi is never born with a strong QS platform. It was mainly a substitute of classical Ethernet, CSMA/CD. So we modified CSMA/CA of the Wi-Fi to support QoS, but not same as of the range of LTE. But femtocell picocell is a classical or the new is a evolution from the 4G where QoS is very well defined. But Wi-Fi people are very smart. They're increasing the speed, the raw speed, 1G, 10G, that raw speed. 5-7 users they can cater very well. But for end-to-end, in the long run, Wi-Fi will be substituted by this femtocell picocell. Another thing will happen for your information. There is a two spectrum, license-free and licensed. And in the license-free spectrum, where the Wi-Fi is now occupying, there those LTE and 5G access points will come, femtocell picocell. That 3GPP has accepted last year to develop the standards in that direction. So then Wi-Fi will get the real challenge from the people. Any other questions? So thank you very, very much.